I feel that with these two resource persons who are really expert in the field will help us to understand the problems of flood as well as how to manage them. And then I think this is, as I told, this is a curtain raiser only, and we can carry on from this point onwards. And the next whole year, I think we'll be devoting ourselves in the flood management and erosion control issues with the help of resource person from the NIH as well as other organizations. And I hope that these 2 days training program will be enriching to all the participants of the entire country. And with these words, I welcome once again to all of you. And then thanks to the resource persons, especially Chakraborty Sir, for agreeing to help us in conducting this online training program. Thank you, everybody.
Thank you, sir. We would like to give a sincere thanks to Biswajit Chakraborty sir, Scientist G, Head of Central Flood Management Study, NIH Patna. Sir has supported us throughout the last 2-3 days in preparing the modules as well as preparing for the training program. So thank you for your support, and I hope we can go along a long way collaborating with Neriwalam and NIH in future also. I would also like to say to our resource person that the lectures that will be delivered online will be recorded. So if you don't mind, if you have any objections, we will stop recording. But with your due permission, we are recording your versions, your lectures, and so that we have a record and we can use these later on when we are not physically or online. If there are some technical problems, we can use those online recordings for wide dissemination in the country. Now, sir, I would like to call upon Dr. U.M. Hazarika, the coordinator of this training program, to say a brief background about the training, sir. Sir, please, on the line, sir. Or we have an announcement, sir. We have also shared the present, the current, the present ongoing program on the YouTube also. Link is also shared. Net check, na? At the chat box. The link is given at the chat box. So those who are not willing to join the online, they can see the YouTube also at their own convenient place and time. Thank you, sir. Sir Hazarika, sir, I would like to request to say a brief words regarding the technical background about the training program. Sir, please.
Thank you, Dr. Priya. Am I audible?
Very much, sir.
So, respected Director Neriwan, or respected resource persons and head flood management, National Institute of Hydrology, Roorkee, and Dr. Pankaj Moni, Scientist Chef, Flood Management Studies, National Institute of Hydrology, and eminent participants from all over the country, from north to south, east to west, and also northeast region of the country. From the number of participants registered in the program, we could realize the relevance of the program, how it is, how much it is relevant task management and whole. So I'd highlight some points regarding the subject of flood management and erosion that these are the two major problems faced by the country are this drought and flood. And getting India's water availability mostly comes from groundwater and surface that accumulates as a result of due to climate change. It is thought that there may be more intense monsoon, but less overall rainy days and a decrease in precipitation in some regions of the country. This gives rise to shorter period of intense flood, arid period. As these weather events become more frequent, water availability and resources become increasingly questionable. Floods as well as human waste makes limited resources. Inefficient practices have further reduced both the quality and quantity of the resources. The stability and reliability of glacier-fed rivers, such as the Indus and Gro, become challenges. Flows increase, high temperature, high temperature springs, possibly causing banks to burst. In many cases, in case of northeastern region also, which is abundant in water resources, one third of India's runoff flows from northeast to Brahmaputra and Barak rivers, and there is a substantial unutilized groundwater resources. The amount on water resources impose severe distress and cost on the region through frequent flooding that this needs to improve economic development of the region as well as the country. The flood problem is further aggravated by riverbank erosion, which destroys about 8,000 hectares on an average of riparian land along the. So regarding approaches to the flood management in the country, there are the practices which are largely focused on reducing flooding and reducing susceptibility to the flood damage through a variety of interventions. Different measures have been adopted to reduce flood losses and protect the floodplains. Depending upon the nature of the work, flood protection and flood management measures classified structural measures and non-structural measures. Regarding structural measures of flood management, which brings relief to the flood-prone areas by reducing flood flows and flood levels. These server created behind dynamic procedures. A natural reparation suitably improved and regulated if necessary. By diversion of a part of peak flow to another river or basin, where such diversion would not cause appreciable damage. Again, by constructing a parallel channel by passing particular town or reach of the river prone to flooding. Regarding structural methods of flood control anti-erosion which do not reduce flood flow but reduce spillover of the water, these are the embankments which artificially raise the effective riverbank and thereby prevent spilling. Then channel and drainage improvement work which artificially reduce the floodwater level so as to keep the same confined within the riverbank and thus prevent spilling. Then anti-erosion measures which prevent further loss of valuable land, river channelization works, clean and graded rivers to flow in their course, further loss of use, siltation. Also, non-structural measures or the flood-prone flood management are to mitigate the adverse impact of flood of the disseminating advance warning of incoming flood to flood forecasting system and facilitating timely evacuation of the people to safer grounds and discouraging creation of valuable assets, settlement of the people in the areas subject to the frequent flooding and enforcing floodplain zoning. So in our course, we therefore included the estimation of design flood, which are required for designing of various flood management and flood structures, and also techniques to develop the flood hazard zones, which is a non-structural measures in our course today. These deliberations should be made by Dr. Pankaj Moni, and I request all the participants to interact and interact even during interaction session also. Half an hour is kept for the interactions, and all participants can interact during that time. So, and how to go ahead with the various structural and non-structural measures to have a effective plan. Urban flood is also another problem and increasing trend, and it poses a great challenge to the city administration and urban planners, not only in our country. The problem associated with the urban flood ranges from relatively localized incidents to the major ones, is being inundated from a few hours to several days. Therefore, the impact can also be widespread, including temporary relocation of people, damage to civic amenities, deterioration of the water quality, and risk of epidemic. The problem posed by urban flooding are quite challenging and aggravated with continuous climate change, with its adverse impact affecting variation in rainfall, intensity, inter-region distribution of rainfall. Unplanned development and encroachment also aggravated the situation, and our water courses have muddled with the natural streams and water courses. As a result of this, runoff has increased in proportion to urbanization of the watershed, causing urban flood. In the recent years, the challenge posed by urban flood, coupled with rapid urbanization and climate change, requires altogether different approach in comparison to river and flood. National Disaster Management Authority has brought out detailed guidelines for management of the urban flood to boost the efforts for urban flood disaster management and strengthen the national vision of moving towards a more proactive pre-disaster preparedness and mitigation and centric approach. These guidelines contain all the details that are required by the planners and uh, to develop policy and master plan for the areas. So during our course, in the second day, there's evaluation of riverbank erosion, including river flow model, urban flooding models. This will be discussed by our eminent scientists, engineer Biswajit Chakraborty, scientist F, Center for Flood Management Studies. So I will be delivering uh, um, uh, for 2 hours, and all participants may interact to know about the popular methods of flood management. So actually, this providing absolute protection to all the flood-prone areas against all magnitude of flood is neither practically possible nor economically viable. So such an attempt would involve high cost for construction on operation or maintenance, and a pragmatic approach in flood management is to provide a reasonable degree of protection against the flood damage at economic cost through a combination of structural and non-structural measures. The state government, union territories have largely focused on structural measures for their investment, and the Ministry of Jal Shakti Government of India under flood management program has been providing financial assistance to the states for such works in critical areas subject to budgetary allocation, in which the non-measures of flood forecasting, warning, and interstate measures are also included to enable the state government to take the advance action and measures save the valuable life and property from the damage of flood. So I request all the participants and expect that they will participate actively and interact during introduction session, and also I request the resource persons to deliver today on the topics. Yes, thank you. Thank you all.
Thank you, sir, for your brief introduction about the technical programs for today and tomorrow. I would like to request, if sir permits, B. Secretary sir, NIH head, Patna, to say a few words for this two-day online training program. So this is the first collaboration between Neriwalam and NIH Patna, though we have met many times online in the meetings and all. But it's the first technical program that we are collaborating with Patna, NIH Patna, and Center for Flood Management Studies Patna is the right center where we can discuss about the flood management, not only in Bihar, but also in other parts of the country, because they have done lots of studies regarding the flood management. So would you please say a few words regarding this training program, sir, please?
Good morning to all of you. Thanks to the director, Neri Wong, the course coordinator, Dr. Victoria, for associating us with your program, with your training program. Since 2018, we had been associated with Neri Wong for various kind of training program organized by them. Initially, we started with introduction to hydrology, and that was spanning for a duration of 5 days. That was offline training, and this time we are meeting virtually for online training. Although one-to-one interaction matters, and that is very effective, but nonetheless, here, what I see here is a number of participants now. It's 92. It's an amazing figure, starting from north to south, east to west of the country. As far as the flood menace is concerned, definitely there is a question mark whether we can stop flood. No, but definitely there is a we can manage somewhat. We cannot stop, but we can manage. So let us, we have done a few studies, we'll try to share. It is not that we have done many studies, but whatever studies we have done, we'd like to share with the participants, and we'll try to get feedback from them. So without wasting much time, I would now request my colleague Dr. Pankaj Mani to start today's program. There are 2 lectures and with a duration of 1 hour each, and it will be followed by half an hour discussion. So with these words, I thank the organizers, and again thank all the participants for showing their interest and associating them with the program of NERU. Thank you so much, Dr. Victoria, and the director, NERU. Thank you.
Thank you, sir. Now I would like to request Dr. Pankaj Mani, sir, to say a few introductory about himself, and then we will go ahead with the classes. Sir, are you set? All set, sir?
Yes, madam. Am I audible?
Yes, sir. Very much, sir.
Okay, so I'll start, madam. Thank you, Director Neribaum, Victoria, madam, Dr. Hazarika, and Chakravarti sir for giving this opportunity to share my views and my studies on design flood estimation. and very good morning to all of the participants. The first basic thing is, am I audible to all of you so that I can express myself to the audience? So first thing I must know that am I audible? Madam, am I audible to?
Yes, it is audible.
Sir, in the chat box, they have said yes, yes.
Okay, thank you, madam. And second thing, now I'm going to share my screen, so that also is very important. So if my screen is visible, sir?
Yeah, it's visible now.
Okay.
Yes, sir,
thank
yes,
you.
sir.
So I am Pankaj Mani, working as scientist F at Center for Flood Management Studies, National Institute of Hydrology, Patna. And today we'll discuss this design flood estimation. Basically, when we call flood or when we say flood, so what comes in our mind is it is an event when the land or the area which is inundated, otherwise it remains dry, means the land which generally remains dry got inundated, so we consider this as a flood. And we do lot of activities within those flood, or we call it floodplain area. So within that floodplain area we do lot of activities, lot of infrastructures are there. So whenever we have to design any structure within those flood region or the flood inundated areas, we have to select a quantity of the flood for which we are going to design that structure. And how we can arrive at that quantity of the flood or that magnitude of the flood, that is basically the design flood. Design flood means the flood for which we are going to design a particular structure. So that is the design flood estimation, and that we are going to discuss in the lecture. So this is very important in the sense that this will be the flood for which or a specific flood that will be adopted for design of the structure. And how can we get the idea of those flood? What could be the idea or what could be the magnitude? So basically we are not adopting any normal flood. We are adopting some extreme values, means based on our experience or based on our historical data for that area, we try to find out what could be the possible extreme flood that may occur in that area. And again, depending upon the nature of the structure or the importance of the structure, we have to decide what could be the magnitude of the flood. So we can go for a very high flood for a small structure also, but what will happen, that will be a very costly affair. So we have to be economical also as well as safe also. Safe in the sense that if that flood, that magnitude of flood occurs, the structures should safely pass that flood and without causing any harmful effect on the flood as well as because of the flood on the surrounding area. So that way we have to decide the design flood. Now, what is important in this one is how we can get idea about that extreme flood. So there can be different technique, there can be different way to find out those things. And one of the technique that we will discuss, we call it a deterministic flood and or probabilistic flood. So how we are going to get it, that I will explain it. Now see what is happening, what I said, that based on our historical flood event only, we get the idea that what could be the extreme flood. Now what is happening within a catchment, there is some rainfall is occurring in the catchment, and then the catchment itself is giving some response to those rainfall and resulting into the development of the discharge or the flood hydrograph at the outlet of the watershed. So this is the rainfall occurring in the watershed, and there is a catchment response because most of us are working in the field of hydrology or water resources. So we can think of the catchment response. If I say unit hydrograph is the nothing but the catchment response. when 1 centimeter of rainfall is occurring all over the catchment, then what will be the outflow? So that is the unit hydrograph. So this is one type of catchment response. So this catchment response transforms the rainfall into the discharge at the outlet. And this discharge, how we describe or how we measure is flow versus the time. How the discharge is varying or increasing and then reaching the maximum and then again decreasing. This nature will depend upon the rainfall that is occurring in the catchment. So what we are going to have in our data set means whatever design value we are going to estimate will be based on the observed values. What type of observation is available? We are observing the rainfall data. So we have the rainfall at one or several stations within the catchment. Then second, what we are observing at some of the site, we are observing the flood hydrograph or this discharge versus time. Or sometimes we are observing water level and then we are having the rating curve. Rating curve means the water level versus discharge relationship. So based on those also we can develop the discharge at the some outlet. So these are generally the available data set available in the water set. Sometimes it may also happen that we don't have any data within your catchment. Mostly it occurs for a small structure. Say you are designing, you have to design a culvert or you have to design a road bridge. So if it is a very small structures, then the catchment also will be very small. Then we don't have any observation in those sites. But what is available, we generally we have the rainfall data, means these are the widely spread data available for the region. Discharge may not be available, but rainfall in the surrounding area is available. So we have some analysis for the rainfall, and then we will use the catchment response in terms of unit hydrograph to arrive at the design flood at those this culvert or breezes, whatever we are saying. Means for gauged also we have to go for the design discharge, as well as for the ungauged catchment also we need some mechanism to have design discharge. So based on the availability of the data, we should go for the appropriate techniques. There are several techniques for gauged as well as ungauged. Now again, what is happening if in this catchment, say for example, we are observing the rainfall data and we know that this is the somehow, say for example, if we know that this is the maximum rainfall that is possible over this area by some mechanism, I know that this is the maximum rainfall that is going to occur in this area. It means what I am saying that it is a deterministic type of approach, that rainfall I have fixed, that okay, this is the maximum rainfall that is going to occur. And then using this catchment response, if I am getting the flood hydrograph here, this will be a deterministic or the fixed type of flood hydrograph at the outlet. So in means there are two methods of design flood estimation. One is deterministic and second is probabilistic. So in deterministic, by some technique, if I know that this is the maximum rainfall possible in that area, so corresponding to that, we call it PMP, probable maximum precipitation. And corresponding to those PMP, using this catchment response, if I compute the flood at the watershed outlet, that we call it PMF, probable maximum flood. So this will be our deterministic approach to find out the design flood at the outlet. Now, what is happening if based on this observation in the catchment, if I find out what is the maximum rainfall that has occurred in the past. So when I am saying maximum rainfall, and it is slightly different from PMP. In PMP, what we are doing, PMP is whatever maximum has occurred, but again we are going to maximize it by introducing more conducive climatic condition. and hydrological condition. Climatic condition means, okay, if say at the time of maximum observed precipitation, if there was 100 centimeter a particular day has occurred, say then on that day the moisture content in the air was only up to 90%, say, or 95%. What would have been the rainfall if it is in place of 95, if it is 100% moisture? So that way we are maximizing it in the PMP. But based on observation only, if I say that, okay, this is the maximum rainfall that has occurred in the catchment, and if I am using those data, then what I am computing is the maximum flood that has occurred at that watershed. So this is again similar to the SPF, what we call standard project flood. Standard project flood is based on the observed data for the maximum event, and PMP is when we are maximizing those maximum data for climatic and hydrological condition. We in hydrological also we can consider that all the depression in this watershed are already filled up. The soil is already 100% saturated. So whatever rainfall is occurring, that is all going to convert into the discharge at this outlet. So this way we are maximizing this hydrometeorological condition in PMP. Now, second approach is for probabilistic approach, means based on our rainfall data or the observed discharge at the outlet, we find out what is the probability of a particular flood occurring at this site. Means what is the probability that this magnitude of flood occurs once in 20 years, once in 25 years, excuse me. Hello sir. सर मैं एक लेक्चर में हूँ, सेकेंड हाफ में फोन करना आपको. So when we add the probability of this flood, occurrence of the flood, then we call it means probabilistic approach, and that we carry out using the frequency analysis. So that also we will discuss. So in design flood, we are having the PMF, the flood expected from most severe combination of critical meteorological and hydrological condition possible in the region. And when we call SPF, standard project flood, so this is also expected from severe combination. It was the most severe combination. It is the severe combination of meteorological and hydrological condition, considering the characteristic of the geological area. Generally, the maximum observed data we consider for SPF, and when we maximize those observed data, we go for going to get the PMF. And then for the specific frequency, as I said, based on the probabilistic analysis, we go for find out the flood of a specific frequency at a particular site. So here, what we are going, we can have the probabilistic approach or the frequency analysis approach on the discharge data as well as on the rainfall, because in some of the site we have the flood data or the discharge data available, but consider sites where we don't have the any gauging sites are there, then we go for the frequency analysis of the rainfall data, because this is widely available comparative to the flood data. And then once we have the rainfall frequency analysis, then we use some catchment response, and then we convolute the catchment response and the rainfall of a specified frequency to get the flood of the specific frequency. So this way we go for the design of the estimation of the design flood. So again, it will depend upon the availability of the data. If we have the stream flow data or we have the rainfall data. If we have the stream flow data, then we are having different equation. Empirical methods are there. Earlier it was used. Now flood frequency methods is there, and then flood envelopes are also there. As I said that flood envelope means whatever historically extreme flood has occurred, you prepare the you consider all those data, and that will be the envelope. Means now I'm going to design depending upon the importance of the structure within those envelopes only. So that is flood envelopes. And flood frequency, generally frequency analysis that we'll discuss. We compute the flood of a specific frequency or recurrence interval, and for that we are going to design a structure. If we are having the rainfall data, so again for rainfall data we can have the probabilistic and deterministic. In deterministic we are having either the PMP or standard project flood. In probabilistic, based on flood frequency analysis, we can find out the rainfall of a specific return period. So these will be the design rainfall. We can compute based on the available rainfall data using either probabilistic or deterministic approach, and then using some catchment response like rational or SCS or unit hydrograph or routing, we are going to derive the flood hydrograph. So this is the basic things, and then lot of intricacies are there. We will discuss some of the things in the next slides. We are going to see the case examples also. Now, what should be the criteria? Means a structure is to be designed for which type of flood. So if means what could be the magnitude of the flood for a specific structure? So how we are going to decide? So if the structure is very large and very important, then obviously the design flood will be higher. The criteria for design flood will be higher. And if the structure is small, so the criteria will be comparatively smaller. So depending upon the economic value of the structures and importance of the structures, as well as the hazard associated with those structures, you have to consider the magnitude of the flood. So generally BIS codes are there that defines or that has given the guideline to adopt the design flood for specific structures. So this is for the in case of the dams, if it is a small one, so where the gross storage is between 0.5 to 10 mcm and hydraulic head 7.5 to 12 meter, then it is called the small structure. And for a small structure, the design flood should be the 100-year flood. So this is based on the probabilistic approach or flood frequency analysis approach we will use, and we will find out what would be the 100-year flood. But if it is the structure is intermediate one, where the gross storage is between 10 to 60 mcm and head is also 12 to 30 meter, then we call it intermediate structures. And then for this structures, we have to go for intermediate design flood, and that is the standard project flood. Standard project flood, as I said, that generally it is considered as 80% of the PMF, or it is the maximum observed flood in that area. So this is the standard project flood. And if the structure is very large, then we have to go for the PMF flood. So these types of criteria are also there for small structures also. For say for you are designing a small culvert, so there also we have there are BIS code or guidelines what type of design flood should be adopted. For example, if I am designing, I have to design an embankment. So if the embankment is passing through some urban areas, then we should go for 100-year flood. If this embankment is passing through the agriculture area, then it can be designed for 25-year flood. So for different structures, some guidelines are there, and from there we have to get the criteria what could be the design flood for those structures. Once you get the criteria, then for that magnitude we have to find out what could be the that magnitude, what could be the flood estimate corresponding to that magnitude. That we are going to understand the mechanism in this lectures. So first we will discuss using the flood frequency analysis. And flood frequency analysis, generally, as I said, we are analyzing the extreme values. So this frequency analysis is the this extreme value analysis. This could be the maximum flood, or it could be the drought. Drought is also extreme. So the way we are analyzing the maximum flood, same way we can also analyze the drought also, because that is also extreme values. So this is the technique, almost similar technique is applicable for extreme as well as the flood and droughts also. Now, the magnitude of extreme event is related to their frequency of occurrence. It means higher is the frequency, smaller will be the magnitude. If I say what is the magnitude of the flood that is occurring every year, so that flood will be smaller in magnitude. If I say what could be the magnitude of the flood that occurs at least once in a 5 year, so the higher is the lower is the frequency, then higher will be the magnitude. So this way the frequency of occurrence and magnitude are inversely proportional, and we have to find out basically this depending upon the frequency we have to compute the magnitude. Now the objective of frequency analysis is to relate the magnitude of event to their frequency of occurrence through probability distribution. How can we find out the frequency of occurrence? We have to find out based on the available data, whatever extreme events data we are having. So first we are going to find out what is the probability distribution. There are several probability distributions defined in the mathematics. We have to find out our data is fitting to which probability distribution. Once we are able to identify our data set best fitted for a specific probability distribution, then that specific probability distribution we will use to predict generally what is happening. We are having a data for a limited period, say 30-year, 40-year, 50-year only, or annual maximum rainfall at a particular station, or annual maximum discharge at a particular gauging site we are having. Now, based on these 30-year or 40-year data, what we are interested? We are interested in particular gauging site we are having. Now, based on these 30-year or 40-year, we are interested. Hello. Am I? Your voice is not very much audible. Can you repeat what you are saying? Hello. Hello. Am I audible?
Yes, sir.
What was the question? I could not means audible. It was not audible. Can you repeat? Probably he's disconnected. Next time when you connect, please ask me. What I want to say that generally we are having a very limited data set, means for available for a smaller length comparison to the probability for which we are looking for. Say for example, if I say that I have to design an embankment and I want to know what could be the design discharge for that embankment. So for that, the guideline says, okay, you need 100-year flood. Means the frequency of the flood should be 100-year. So what could be the magnitude? That is my objective to estimate. Now I have the data only for 30 years or 40 years. So how we are going to use this 30 or 40-year data to predict flood for 100-year data? So for that we need a distribution. We need some forecasting technique. Now, what is the forecasting technique? First, we will try to fit the existing data set in some probability distribution. There are, say, several probability distribution. We will try to fit it into many probability distribution, and then we will try to find out which distribution it is best fitting into. So that way we will find out the best fit distribution for my data set. Once I got the distribution set or identified my best fit distribution set, then using those parameter of those distribution, I will project my data set for 100-year, 50-year or 500-year, means whatever frequency you are looking for, we have to project those those data set based on those identified probability distribution. So this is what we are doing in frequency analysis. And am I audible?
Yes, sir. Yes, sir.
Hello, am
Yes,
I
sir.
audible?
Audible, sir.
Okay, okay. Sometimes it appears no one is saying anything. So this is what we are doing in the frequency analysis. Now, for the extreme events, we have to, first thing is, we have to consider that all the events means when I am saying we are discussing here the either the rainfall frequency analysis or discharge. Rainfall, again, for extreme value analysis or related to the flood, we are taking the maximum values. So discharge also I am taking the maximum, means peak. Means if I am taking the daily data, means what is the maximum rainfall that is occurring in one day. So say for 1920 I have year 1920 I have the 1 day maximum rainfall for a particular station. Say for Guwahati I have the 1 day maximum rainfall data for say 70 mm. So this is the one data. Again for 1921 I have another data, say 76 mm. So this is the second data. So 1 day maximum annual series for rainfall I am taking as my input for the analysis of extreme value for rainfall, frequency analysis for the rainfall data. So say 1920 to say 2020 we are having the 100 entry or 100 values of 1 day maximum rainfall on annual basis. So it is said that we consider all the data as random, means the rainfall that has occurred in 1920 is random. It is not linked anyway with the rainfall that has occurred in 1921 or 1922. So all individual data set has to be random. And second, that it is assumed that they are independent and come from identical distribution. Means the extreme value 1 day maximum rainfall of 1920, it follows the distribution. Say I'm saying for example it is following normal distribution. So the data set of 1920 is following normal distribution. So in 1921 also the 1 day maximum rainfall, it is also following the normal distribution. Means all the data set are independent to each other and they are following the same distribution or identical distribution. So these are the assumptions in our analysis. It can be the rainfall, it can be the peak discharge, means annual maximum discharge also at a say gauging site like Pandu. So what is the maximum peak discharge that has occurred in say 1960? So that is a random. And what is occurring in 1961, 62, 63? So they are not linked with each other. So this way, these are random and all individual values, they are following the same distribution. So these are the assumptions for this one. So how we are defining the return period? Say a random variable is X. What I said, either 1 day maximum rainfall or 1 day maximum discharge at a particular site. And this is the XT is the threshold level. We are trying to find out what is the XT. XT means say this is the random variable corresponding to T year, means 25-year return period, or it could be 50-year, or it could be the 75-year or 100-year. So this is the threshold value which we are interested in, which we want to find out. Now extreme events occurs if X is greater than XT. Means this is what we consider, means we are considering this is the maximum value for every year that will be considered in our analysis. And this XT will be whatever we are trying to find out. For that, what could be the time of occurrence? So this will be the occurrence when a particular or the specific event will be higher than that XT. Say I am finding out XT for 25 year. So for that, what could be the X? What could be the variable? Means any event that has occurred more than, say, in a span of 25 year, at least once higher than that 25-year value. So that will be the recurrence interval. Whatever time we are considering, And then corresponding to this ET, that will be our return period. Average recurrence interval between events equaling or exceeding a threshold. So how we are going to compute? If P is the probability of occurrence of an extreme event, then time period, that is the return period, this is the relationship. Relationship is equal to T is equal to 1 by P, means what is the probability if we take the inverse of that P, this will be the return period. So we are going to compute this ET and for any particular T, means a return period, we are interested in 25 return period or 100-year return period. So what could be the probability, and corresponding to that probability, what could be the extreme event? That is what we are interested in finding out. And again, some relationships are there. If P is the probability of success, means this is the probability that an event is occurring, then 1 by P will be the probability of failure. Means if P is the probability that a particular amount of flood is occurring, then 1 minus P will be the probability that, okay, there will be no flood higher than that value. So that will be the 1 minus P, means it is the probability of success, then it will be the probability of failure. And then if this particular is in a sequence of say n years, means say I am trying to find out what is the probability that a 25-year flood occurs, what will be the probability? So the probability that a flood greater than 25 year will occur, that we define by small p. It is the probability that a flood greater than 25 year will occur. So what is the probability that it will not occur? So that will be 1 minus p. And say in a span of continuous n years, if this is not occurring, so what will be the probability? So first year it is not occurring, second year also it is not occurring, third year also it is not occurring, then the probability will be multiplied. So this, what is the probability that this event will not occur in a continuous n period, n years? Then we have to multiply it 1 minus p into 1 minus p into 1 minus p n times. So this will give you the probability that a particular event P will not occur in a span of 25 years. Then what will be the probability that at least it will occur once in a span of 25 years? So this 1 minus P to the power n, because we are multiplying it with the n times, that will be the probability that it will not occur. And what will the probability that it will occur? So again, it will be 1 minus P to the n. So this will be the probability that any event higher than the xt will occur at least once in a year, will be 1 minus 1 by P to the n. So this is the relationship between the T, n and P, that an event occurs at least once in a span of n year. So this relationship we are going to use or utilize to find out the event, magnitude of the event. So now first thing what we are interested in, first thing we have to find out, based on our data set, what is the best fit probability distribution. Once our probability distribution is defined, then we have to find out what is the parameter for that distribution. And once the parameter is decided, then we can use this type of this, I'll explain through the figure, this type of relationship to find out any xt, and this xt will give you the magnitude of a particular event having the return period of t. So say I have the first we consider this is our probability distribution. When we plot the probability over the event, this is the occurrence of the event on the x-axis, and this is the probability. So what we said that the extreme events, smaller events occur more frequent. You can see the smaller events are, these are the smaller events. So these are the probability, and these are the higher events. So this is having the peak value, means corresponding to this peak value, we have the probability is this one, and area under this curve will give you the probability for any event. Say I want to find out the probability of this xt. So what will be the probability of this xt? This will be the area under this curve. So probability of any event, if I'm interested in greater than xt, this is my xt. So all the area, this I'm interested in greater than. So all the area under this curve for greater than xt up to x. So this will give you the probability. If I'm interested in any x smaller than xt, then this will give you the probability of this area under this curve will give you the probability for any event smaller than xt. So this relationship we are going to find out, where xt is the event magnitude we are interested in, kt is the frequency factor we will try to find out, t is the return period, x bar is the sample mean. Again, based on our data, we can find out what is the mean value, and this is the standard deviation. This KTS means this is the standard deviation. So what we are interested in, finding out the relationship between the return period and magnitude, and disasters generally follow the magnitude frequency relation, which means that even with a smaller magnitude happen more often than events with larger magnitude. Means larger events or larger magnitude events occurs very rarely, but small events occurs very frequently. We call it, say for example, I call it what is the annual average flow. Annual average flow, it is almost occurring every year. So the return period of our annual average flow will be smaller. But if I say probable maximum flood, the frequency of probable maximum flood, if we try to correlate, it will be very high comparison to the annual average flow, because annual average flow, it is occurring almost every year. So smaller magnitude events are return period are smaller, but extreme values return periods are higher. This relationship also being used. Now there are different types of probability distribution depending upon the different you can say events in the nature. They follow some of the means based on those experiences or nature of those disaster, they find out which distribution these are following. For example, lightning is a random in nature and it does not follow any distribution. Snow avalanches are seasonal and diurnal, it is again random. Earthquakes are following normal distribution. Tornado is again seasonal, but it is following negative binomial. Landslide irregular. For flood, we can see it is a seasonal, and it is following Markovian, gamma, and log normal distribution. So similarly, for coastal erosion and drought, it is again exponential gamma and binomial gamma. So different natural phenomena, they have the tendency to follow some of the distribution, mostly some of the distribution. So these are just a list which type of disaster is following this type of relationship. But again, you have to analyze your data set with the available distribution to check whether this is following or not. These are the simple guidelines, but it doesn't mean that you don't have to analyze. First, we have to analyze our data set to identify the best fit distribution. So again, the probability it is described as the relative frequency which an event occur or will not occur in the long run. So this way we are defining the probability. It is measured on a scale ranging from 0 to 1. So probability will occur on 0 to 1, and 0 means there is no probability, it is not going to happen at all. But when I say 1, it means certainly it is going to happen. So this is the scale of probability. and some of the events we have tried to just for understanding that what could be the event and probability relationship. That, for example, is it possible that you can swim across the Atlantic? So it is highly improbable. So it is also impossible. So we can give the probability scale 0, and the probability that you will win the lottery, it is of course it is there, but this lottery organizer, they are this lottery organizer, they are means they are doing lot of exercise and lot of background things, so that there is a very little chance to get any one winner. So that is also very less. But when I dash, I say throw a coin, what will be the probability that the head will come down? So again, it is a equal probability. So either there will be head or there will be tail. So this is almost 50-50%. What is the probability that a man will be taller than 1.7? So again, these are the means not very rare things. Many people are more than 1.7 meters. So there is a probability is higher. And what is the probability that one will retire from his service? So it is absolutely certain things that everyone who is in service is going to retire. So this way event are means given the scale 0 to 1 based on the probability of that occurrence of those events. So similarly, our natural events are also there, and we have to find out what is the probability. Say if it is 25-year flood, so within a span of 25 year, what is the probability that this event will occur? Within a span of 50 year, what is the probability that a flood of a particular magnitude will occur? That is what we are interested. So this way we are trying to find out the probability. Again, there are some terms that we'll like to discuss here. Is first is hazard, likelihood, and probability. Hazard is the probability that a particular danger or the threat will occur within a given period of time. Say I am saying a 25-year flood. So this is the hazard, 25-year flood. What is the probability that this flood will occur in a particular time? Say I have designed a embankment for 25-year flood. Now I'm interested that, okay, in next year, 10-year, what is the chance that this 25-year flood will occur? So that way we are trying to find out the hazard. Then likelihood is the conditional probability of an outcome given a set of data, assumptions, and information. So in addition to the data set, we also have some similar type of events are occurring in the nature, and also some correlated events are there. So based on those, we are trying to find out the likelihood. And then probability is the, it is the as I said, it is the measure of certainty, degree of certainty, and it varies from 0 to 1. And it is an estimate of the likelihood of the magnitude of uncertain quantity, or the likelihood of the occurrence of the uncertain future events. And then the annual accidents probability. This is the probability that an event of a specific magnitude will exceeds in any year. So annual accidents means at least once it occurs every year. So that we are going to find out. So that is the annual accidents probability. Now, for example, we come to the actual data set. Say this is my data set for discharge or rainfall, whatever you consider. These are the data for continuous 20 years period of time. And this is you can say we have 6 values in every year, or 5 values in every year. So you can say these groups are for 1 year data set. So for every 1 year we are having you can say this group of lines. This shows the magnitude on this y-axis, and this is the for a particular year. So for this particular year, these are all the data set, and this with marker we can say this is the maximum value for a particular year. So when I say this is the complete duration series means whatever data is there for the entire time period that we have plotted. So in complete duration series, there will be all the data available. Now, when I say that, okay, partial duration series, if I say that, okay, we are not interested in this smaller values, we are interested in values higher than certain amount. Say I'm interested in values more than 40. So in this particular year, we have 3 data set more than 40, this one, middle one, and this with marker. So these 3 data sets. So partial duration series means there will be a base value will be defined, and all values higher than those base value will be considered for the partial duration series. When I say annual accident series, annual accidents means within the data set, what is the maximum value that is occurring in the particular year. So this is the maximum annual accidents. This is the annual accidents. This is the annual accidents. So these are the annual accidents values for a particular year. But when I consider say 50 as the this series, so this 50 also if I include, then this will be the partial duration series. So annual accidents means we are going to take one value, one max, that is the maximum value that has occurred during a particular year. So that will be the annual accidents value. So there can be some annual accident series more than a particular means values. Then we have the partial duration series as well as annual accident series. So some of the frequency analysis we are going with the only the annual series, and some of the frequency analysis we are going to have a partial series also, because some of the two events has extreme events has occurred in a particular year. So that also is to be it is better to consider those two events that has occurred in that year. So depending upon the nature of the analysis, we can use those ones. And then say only if we are going for extreme value analysis, then the extreme value analysis is nothing but the only the extreme values in a year we are going to use. So only the maximum value we are going to use. In annual accidents, if we are giving a threshold value or a cutoff value, so all those value will be used. And in extreme values, annual maximum like things, that only peak value we are going to things. So for annual series, interval will be 1 year. For annual maximum series within 1 year, what will be the largest value that we are going to use? And for annual minimum series, the smallest value we are going to use. So that we can use for drought analysis, or when water availability or something, this type of analysis is required. We are also interested in finding out the lower value also. Sometimes it requires. So for flood, generally we are going for the annual maximum series. So these are the input. This will be the input for our frequency analysis. Now we can consider an example, then things will be more clear. Say these are the rainfall or total rainfall that has occurred during this particular year. These are the you can say or 1 day maximum rainfall annual series that has occurred for a particular station during 1917 to 1966. We have to carry out the frequency analysis for this data set. So first what we do is we will make a range for this rainfall, and this range we first find out what is the minimum value, what is the maximum value, and then in how many class we are trying to divide it. So depending upon then that we have defined the range 450 to 500, 500 to 550, like this up to 700. There are 1, 2, 3, 4, 5. 5 classes we have, 5 ranges we have defined. And now we will find out what is the number of event that has occurred with this range, within this range. Means what is the number of year where we have the rainfall values in the range of 450 to 500. So with this data set, we can find out how many values are there. So we can find out, okay, there are 3 years, we don't know which years, but 3 events are within this range. Similarly, this 9 events are within this range, 6 events are within this range, and 11 events are within this range. So this way, from the annual maximum series, we have defined the first range and then frequency for the event during for different ranges. So this is the again for 750 and 850 means these are the ranges for which we have defined the frequency. Now we are trying to plot this range versus this frequency. So you can see this is the range here on the x-axis, and we are trying to find out the frequency, and then we are trying to find out a you can say a distribution for this one. So this is the actual data, and with this actual data we are trying to find out this type of distribution, and we are assuming based on the shape of this distribution this is the normal distribution. Just for its beginning or for simplicity we consider that okay, this actual data is following a normal distribution. Normal distribution, how we are defining this distribution? These distributions are defined through set of equation. That equation will give you the shape of this this distribution. If we have the say on this axis we have x and this is the frequency, so or the probability, so this will give you the relationship or the shape of this curve. So we are assuming that the existing data set is following the normal distribution. Is it clear? Now from the data set, what we are going to find out for this distribution, we are trying to find out what will be the mean value and what is the standard deviation. It is a normal distribution. So for normal distribution, we know the mean value generally. Yes, we'll show you the case study also. For normal distribution, I'm running out of time probably. For normal distribution, what is happening? We this mean value and what is standard deviation, we can find out this a particular event minus the mean value divided by the mean value. So this is the mean value and this is the standard deviation. So this is the pattern, and if it is an we can see that what is the probability that any event is occurring less than this mean value 642. So by if it is a normal distribution, it should be 0.5, because in normal distribution says that bell shape is normal, means around this 0 or mean. What is the probability of occurrence lower than the mean value will be the same, the probability of occurrence of the value higher than the mean value. So the in principle the any event less than the mean value should be 0.5, any event higher than the mean value should be 0.5, and then based on this equation we can also find out what is the probability of occurrence of various this one, and this is the probability of the normal distribution that if someone is saying something that almost 1 sigma is equivalent to 68.3% of the total population, and 2 sigma is 95.4% of the total population, and within 3 sigma all the data almost 99.7% population will cover. So this is the all the event between the sigma will be 68.3, within 2 sigma it is 95.4, and within 3 sigma almost 99.7% events will be covered in this one. These are the probability of the normal distribution. Now we'll see these are the probability of the normal distribution, means these are the standard. If we consider it as a normal, so this should be the standard for this data set. But what is actually happening in our data set, let us see. So our total events are 50. So what is the probability of events less than 642? For normal it should be 0.5, but we will say 0.5 means out of 50 it should be 25 values. But actually how much is happening, we can see in all values less than 642, so we count, we will find that it is 21. Similarly, if it is higher than 652, it normal means the standard prediction is 25, because I am considering it is a normal distribution, but when I count it, it is 21. Similarly, all values lying between this range, that is 1 sigma range, it should be 34. Actually, we are finding out 36. Similarly, within 2 sigma range, it should be 48, we are getting 48, and within 3 sigma range, it should be 50, we are getting 50. Means whatever assumptions we have made with this data set, that should follow this type of pattern, and actually it is following this type of pattern. So based on this type of analysis, we can consider that okay, this is within the our assumption is right or wrong. So then we can say that okay, whatever we have considered, that distribution is good one, and then I'm going to project my data set based on those probability distribution function. So this was my probability distribution function, and this is the cumulative distribution function, and this is the cumulative distribution function for normal distribution. Here we have the probability, and here we have the mean and standard deviation value. We have the equation for these data set, and then we can find out based on our data set, we have find out the average value. And okay madam, I'll tell you. So based on this, we are finding out what could be the say for my data set, I find out the standard deviation and average, and then for any particular event, if I want to find out, I can find out what could be the probability, or for a particular probability, if I want to find out, I can find out the event. So once I know what is the distribution which is best fit in my data set, and this is the so this is again for log normal distribution, and someone is interested in again case study. I'll tell you again, this is also example to understand very quickly. I'll tell you, this is the return period of a rain event over 100 mm per day. Now this is my data set, and I'm interested in knowing that what is the return period of a rain event over 100 mm per day. Now we can see that this is for this data set, we have to find out all the values higher than this 100 mm. So we will mark all the values higher than this 100 mm. So these red line shows all the values higher than this 100 mm, and then we can see that the return period, or you can say the difference of the occurrence of this first event and second year, means first it has occurred in 1936, and next it is occurring in 1940. So how many years are there? So 4 years. The first the time interval between first two event is 4 years. Similarly, for next event, more than 100 year is 1 year. Again, next year is 100 year. So this way we can find out altogether there are 9 events, and what is the duration between these two successive events, that we have find out, and that is ranging from 1 to 60 years. So if we add all those intervals, it is all 41 years. So we have total 8 intervals and total 41 intervals. So average interval is almost 5.1 years. So the return period of 100 mm per day event is at 5.1 years. From this frequency we find out, means this type of analysis we can find out. Then there are different probability distribution. Let us skip it. We'll come to the again some case example. Say this is the annual maximum for 10-minute storm. Find 5 and 50-year return period 10 minutes. So based on our data set, we can find out what is the mean value and what is the standard deviation. There is no problem. Then for every distribution, here we are considering it for this example, extreme value, we are assuming that this is following our extreme value 1, EV1 gamma distribution. This is the EV distribution this is following. So consider my example that I'm considering that okay, it is following my EV1. So first I have to establish that okay, it is following or not, and second, once it is established, then we go for the finding out what could be the parameter for those distribution and how we can predict the values for different return period. So for EV1, you say this is our probability distribution function, and these are the parameter for this distribution. So this is what we are going to find out. Find a flow that has a return period of t years. We are considering EV1. probability distribution function, and this is the cumulative distribution function for that one. Here we are defining this this variable with a new variable y, and this alpha and this u are the parameter for this distribution EV1. So it will reduce to this form. Yt is equal to minus log, again within bracket, minus log 1 minus 1t. So if I want to find out this yt value for a particular t, then we can use this relationship and this relationship to get. So just in this example, x bar we are having, s we are having, and alpha is again, as we can see, this is the relationship for this probability distribution. So we can find out alpha we have computed, and then we can find out u for based on this equation. This is the parameter for a particular distribution. So this we can find out, and then we are interested in 5-year and 10-year. Now we are having alpha value and u value, and t is 5-year. So we put t as a 5-year, we can get y5, and then we are using this relationship to get the return, the magnitude of a particular event with 5-year return period. So this is the x5, we can get 7.18. Similarly, we can get the x50, means 50-year return period value, that is 1.1. So these are the example. There are several other example also we can find out. So using the Gumbel equation. So first, now some practical example I will see, case studies. Nowadays we are using the L moment approach. In L moment approach, we are evaluating our data set for altogether 12 parameter. And you can online there are several programs you can find out. MATLAB programs are there. We can find out for getting this L moment. So you just give your extreme values, say 20 years or 25 years or 30 years annual maximum values, and then it will evaluate your data set. How it will evaluate? It will give you two things. First is L moment diagram, and then it will give you gyre distance statistics. Now L moment diagram is it is the diagram for L kurtosis and L skewness. These are the plot for the standard data. Means these are the standard data. If we plot it, means assuming that okay, these are the distribution, means standard distribution, you will get this plot like this one, and this is my data set. This is my data set, means I'm going to analyze my data set. Then for that data set also it will plot on the L kurtosis and L skewness plot, and then we will find out my data set is lying nearer to which standard plot. So the nearer plot will define you that my data set is following a particular distribution. So once I know that okay, if my data set is nearer to a particular distribution, I will adopt it. But sometimes it happens based on this L kurtosis and L skewness, we are not going to get any particular distribution nearer to our data set. Then in that case, we can go for the ZI statistics. Again, this is also a statistical parameter. And here it says the lowest value, means ZI distance lowest for different distribution should be more, means likely to follow those type of distribution. So this L moment will compute this ZI distance statistics for all 12 distribution, and the list 5 are shown here. So out of this we can see that okay, this is the generalized logistic having the very least ZI distance. So it means my data set is following this one. So now I will adopt this probability distribution as the best fit distribution for my data set, and then I will compute the parameter for this one, JLO, and then I will project my data set to get the return period, magnitude of different return period. This is the example for Pandu site. This we have carried out for one of the study for Brahmaputra River related with GMDA, Guwahati Metropolitan Development Authority. We have the data from right from 1960 to 2017 from different sources. You have some data from Brahmaputra Board, AWRD, and CWC, and then these are used to analyze the best fit, and then based on those best fit, we have computed the magnitude for different return period. So this is nowadays we are using this L moment based frequency analysis. This we can use for discharge also as well as rainfall also. So this is one of the example. So we'll take a 5-minute break before we'll start unit hydrograph approach. If someone is having some discussion. If someone wants to say something.
We are giving a 5-minute break, and after this break, and also we'll continue the class.
Yes, very quickly I'll try to cover this unit. Actually, these itself are means a huge topic. You cannot compile it within a 1 hour duration, and that also generally in design flood we cover 2 aspects: flood frequency as well as deterministic, that is unit hydrograph based. But itself these are very extensive, means descriptions are there. But I'll try to cover these 2, and then we will also do zoning part.
And so some of them have given some questions in the chat box that will be discussed after the class.
Okay, madam. So, okay, we'll start second part of this design flood estimation. And this is called the deterministic approach that I am going to discuss using the unit hydrograph approach. Should I start?
Sir, I think we can start without any delay, like
Okay,
the participants are still tuned in.
Okay.
And,
So again, what is happening in design flood estimate? Earlier, we are using this flood frequency analysis either with the rainfall data or with the flood data. Here we are going for the deterministic approach. In deterministic approach, or the unit hydrograph approach, we are starting from the rainfall, then we are considering whatever losses are there in the rainfall that we have to account for. And then we have to consider the catchment response, how the catchment is responding to the rainfall. And then for frequency analysis in NIH, L movement based one software is there that we are using. It is developed by one of our scientists. It is the technical background is very widely available in the literature, but the module has been developed by Dr. Rakesh Kumar at NIH Roorkee headquarters. Although he's retired, but still we are using those things. So if someone is interested, we can ask, he can ask Dr. Rakesh Kumar to provide this one. There was one question regarding which software. Otherwise, in the net also different several this MATLAB programs are there for L moment based frequency analysis that also can be used. So okay, in design flood estimation, you need hydrograph approach. First, we have to find out what would be the design storm. Again, it can be based on deterministic approach like PMP, or it can be a flood frequency analysis, a rainfall for 25 year or 100 year or 500 year. So that storm we can compute. Then this is the catchment response. For example, unit hydrograph is there. Then design loss is if whatever rainfall we are considering, there will be some losses from those rainfall. Means part of the rain will be absorbed in the depressions, partly it will be evaporated. So for design loss, we have, if you remember, there are several equations are there, phi indexes are there. So based on those, we can find out the design losses. So from design storm, if we minus design loss, we will get effective rainfall. And then this effective rainfall, we give you, we will find out the distribution, means how it is distributed, temporal distribution of this design, this excess rainfall. So that will give you the hydrograph, means time distribution of the hourly rainfall. Within, say, I'm considering 6-hour rainfall or 10-hour rainfall or 24-hour rainfall. So that is the hydrograph we have to compute. And then using this hydrograph, we convolute with the unit hydrograph, we can get the direct runoff. And in that direct runoff, we will add the design base flow. So for that particular catchment, what is the base flow? Base flow is not because of the direct rainfall, but it is because of maybe because of some groundwater or because of some earlier event that has occurred, still some flow is there. So that will be added to the base flow so that we can get the final design flood hydrograph. So these are the steps in this one. We will discuss some of the things. And this is the loss rate. You might have heard about the phi index. This is similar type of this one. Then for finding out the losses, some coefficients are there in this equation, in the previous equation. Rainfall, runoff is some coefficient rainfall. So these are the coefficients. Find out depending upon the soil, what will be the losses, we can find out. And then again, we need the design base flow. So either from the historical event of the flow data, we can find out when the rainfall has stopped, but still there is some base flow is there. So we can take those values. And for ungauged catchment, we can use the table. And this is the table provided by the different region for different rivers. They have given the base flow. So for cubic per square kilometer, depending upon your catchment area, you can find out what could be the base flow. So in your direct runoff hydrograph, you add this base flow to get the total runoff hydrograph. So this will be added to the direct. Now we will first consider the design storm parameter. Design storm is the duration. No, why uniform soil loss? This is not like uniform soil loss. If you have some data, you can use the temporal distribution also. There is no problem. But generally, we are doing it for extreme analysis. In extreme analysis, we consider that the means when you are finding out the design flood, it means you are considering that it is all saturated. So whatever losses are there, it can be considered uniformly. But if some event is occurring for the first time, then initially there will be a lot of losses in the swell, and then once the swell gets saturated, it will come to the uniform swell loss. So that way, when we are designing the extreme events or design flood estimation, we are considering the uniform swell rate, because we are considering the soil to be fully saturated and all the depressions are filled up. So that is what the extreme means. We are trying to maximize our flood. So in design storm parameters, what are the important thing is, first we have to find out what is the maximum depth for which that will be part of the design storm. Means I'll give you example. For 1 day rainfall, I am using extreme value analysis using say frequency analysis. I am using 1 day maximum rainfall. So I have 40 years data for 1 day. Then I will analyze, and using this data, I will find out what will be the 1 day maximum rainfall for 25 year or 50 year. So what I will get, I am going to get a single value, means my 1 day rainfall is say 700 mm. So this is a single value. So, and this is a 1 day. So duration is 1 day and depth is 700 mm. So these two are defined. Now third is, what is the temporal distribution within 1 day, that is 24-hour duration. How this 700 is distribution? Is it possible that all the 700 mm is occurring in the 1 hour or 2 hour or within 3 hours? So that is the distribution, that also we have to find out. And then once generally what is happening in distribution, we get the cumulative value, means within first hour 10% will occur, in next 2 hour, in next 1 hour another 5% will occur, then another 10% will occur, means you will get a cumulative value. Now those cumulative values has to be converted into the incremental value, and then based on those incremental value, we have to find out what could be the sequence of those rainfall events so that we can get the maximum discharge. So this is how we are finding out the hydrograph in the storm parameter, that I will tell you through some example. So say this is by first method is align the incremental rainfall values to match the unit hydrograph formula, reverse the sequence of. Now what is happening, how we can get the maximum rainfall? Say we have one value for 1 day, 700 mm is occurring in 1 day. Then second input we are having, that what is the distribution of this 1 day rainfall within 24 hours. For example, you see this is a hourly distribution coefficient for 21 hour rainfall for the first 12 hours and normalized distribution coefficient for 12 hours. So from field data, we are having SRRG data, means self-recording rain gauge stations are there. From those data set, you find out what is the distribution, what is the rainfall pattern for the extreme rain that has occurred, means 1 day maximum rainfall that has occurred in the region or the nearby area. So from those type of data set, we can find out within 24 hours what is the distribution. These are the distribution coefficient, means for the first hour 19% of the 1 day maximum rainfall has occurred. In next 1 hour, that is the within 2 hours 29% of the total rainfall has occurred. In 3 hours 36% of the rainfall has occurred. So this way we have to find out or the SRRG chart will give you that the distribution, means the hourly distribution of this rainfall, extreme rainfall. So this way, these are the cumulative values. You can see these are the cumulative values. Similarly, if from this distribution, if I want to find out for 12, so these are the first 12 hours, 19 up to 70. So these are again normalized. Normalized means I have to convert this 70 to 100, this on and 19 to 72 on this scale. So this has been again normalized to 0 to 100 scale. This was 0 to 72, this is 0 to 100. So within 12 hours, this has been normalized to again 100%. Now, why we are doing this within 12 hours? Because this guideline says, generally earlier what is happening, if I am analyzing 24-hour data, then we consider it will start right from, say, I am considering 0 hour or 1 hour. 1 hour it will start moving up and peak will be occurring at 12 hours, and then it will start decreasing, and again the minimum value will be on 24 hours. Then it could be found, or it was observed, that this type of pattern is actually not occurring in the nature always, or mostly it is not occurring. What type of event is occurring? It is occurring in, हाँ जगदीश, जगदीश, हाँ हाँ लेक्चर में थोड़ी देर बात करते हैं. So then they propose, based on the observed event, that the actual rain is occurring in 12-hour spells. Means first 12 hour it is occurring, then maybe for few hours there will be no rain, and again in another 12 hours it is occurring. So they propose that, okay, you don't consider 24-hour cycle, you consider a 12-hour cycle. Means this cycle means this rainfall, if we consider, means if we consider, if we plot the rainfall, then it will be a shape of the bell. There will be a shape of the bell. So they consider that, okay, this type of bell, 24-hour bell, is not, means this type of bell within 24 hours. This is my 0 and this is 24. This is what initially we have considered, but they say, okay, no, this type of is not, means always possible. We should consider this as a this type of bell. Means 2 bell in 12 hours. So there is a 2 bells in 12 hours, but my observed data is for 24, because mostly we are having the daily data observed at a station. So we are analyzing the 1 day or the 1 day data, but our pattern is, proposed pattern is 2 bell in a day, means 12-hour bell. So for 12-hour bell, we have to find out what could be the distribution. So this was basically the idea, and that's why we are interested in finding out what will be the distribution for 24 hours. So by 1 day rainfall, we have to divide into 2 spell of 12 hour each, and for each 12 hour we have to find out what could be the distribution. So this is first the temporal distribution. I'll show you some example also, then it will be more clear. Say for some technique, either frequency analysis or from some data, we have get 100-year data as, and I get rid of this. Okay, so for 100-year data, we are computing that 24-hour rainfall value is 28 centimeter. So this is my, either it is coming from some frequency analysis or some table or from some atlas, we are getting this value. Means for your study area, the say 100-year rainfall for that area is getting, we are getting as 28 centimeter. Then there are some other factors also, because you are using a point rainfall data for your aerial distribution, so there is a reduction factor also. So after the introducing the reduction factor, the 24-hour rainfall for 100-year data comes to be computed as 23.786. Now this is the rainfall that is you have computed to occur within 24 hours. Now the guideline says that, okay, this 24-hour data is to be divided into 2 bells. One 12-hour bell for each for 2 duration. So how much rainfall we will consider in one bell? First 12 hour. First 12 hour, we it is proposing that you consider about 70 to 75% of the rainfall. And in the next second 12-hour duration, you consider balance. Means if my total rainfall is 23.86, so in first you consider 72%, that is 17.81, and in next 12 hour you consider the 6.68. So this is the distribution of 24-hour into two 12-hour spell. So this is what we are considering. This is the distribution coefficient which we have computed from earlier data set, and this is the we have normalized on the scale of 0 to 100. And first 12 hour, if it is 26%, so my first value, this 100% for first bell will be 17.18. So this corresponding to 17.18 for every 1 hour, this is the cumulative value. So for first bell, this is the cumulative value of total 17.18, and this is the cumulative value for second well. So this will be again 6.68. So from this cumulative value, you find out what will be the incremental value. Means this is occurring in first hour, this is occurring total in second 6.92 in 2 hours. So what will be the value in the next second hour? This minus this means first hour it was 4.53, but in second hour 6.92 minus 4.3, that is 2.39 has occurred. So that if I add these together, this will be the total value after the second hour. Similarly, if I add 1.67, this value will be the 8.59. Means from the cumulative value we are finding out the incremental value for first bill, similarly for the second bill. So these are the incremental value in 1, 2, 3, means altogether there will be 12 incremental value for first bill, similarly 12 incremental value for the second bill. Now these are the total rainfall in various hours. Now we have to use the loss rate also. So depending upon your study area, if you have the data, you go for computing the loss rate. If you don't have, then you directly go for the CWC guideline. They have, for different reason, they have given some values. So we will directly use those values. And from the total rainfall, we can find out the effective rainfall for hour 1 and hour 2, bell 1 and bell 2. So for bell 1, we have 12 values, and bell 2 also we have 12 values. These are the effective rainfall for 2 spells of the rainfall. Now what it says that the rainfall occurrence will follow the unit hydrograph, shape of the unit hydrograph. What is the shape of the unit hydrograph? Shape of the unit hydrograph is also the generally it is also like this bell type of shape. So we have to keep the maximum rainfall from this one. Say this is my effective rainfall. So what is the maximum value? Maximum value was the 4.18 value. After that we have 2.04 value. And if we see, this is my unit hydrograph. Unit hydrograph is 3 hours unit hydrograph is there. So first 18, then 32, 52, 92. So within this unit hydrograph also you find out what is the maximum value. So we can see 134, that is occurring on the 10th hour. This is the maximum value. Then it says why we are doing all these things. We want to maximize the flood from the rainfall. So how it can be maximized? So here at this hour, the response of the rainfall is maximum. So here we will keep the maximum ordinate, what we have computed earlier. What we have computed earlier is 4.18 is the maximum value. Second is 2.01. Next is 1.32, 0.84. So maximum value we will keep on the peak of the, or the maximum ordinate of the unit hydrograph. So this you can see, this is the maximum ordinate. So we have the maximum value. Then next maximum will be another below the next maximum. These are the ordinate of the unit hydrograph, and these are the ordinate means now what we are doing, we are sequencing our incremental value of the rainfall within the bell itself, so that we can get the maximum discharge or the maximum runoff at the outlet. So this way, the maximum ordinate, we are giving the maximum rainfall value. 132 next maximum, 129 next maximum. This way we are arranging our incremental rainfall in 12-hour bell in such a way that it follows the unit hydrograph shape of the unit hydrograph. Similarly for the second hour well also. Here also the maximum ordinate we will keep below the maximum ordinate of the unit hydrograph. So this way the the incremental values are arranged, or the sequence of the incremental values are carried out, and this is we call critical sequencing. And this is only because we want to maximize the discharge. I will also show you, if we don't consider this type of things, how much data, how much discharge we will get. One example I'll show you. So this is for the first 12 hours, this is for the second 12 hours. Now again, CWC guideline says that once you arrange this one, the critical sequencing, it is observed that if we reverse the sequence, earlier it was 0.37, then 0.6, then 0.6. Now it has reversed. The first value has come in the last. This is the reverse sequence of the effective rainfall. The first value has come at the last. Next, second value has come in the second last. Third value has come in the third last. So this way, whatever sequencing we have derived, that is reversed here. So once you reverse this sequence, similarly for bell 2 also, then it was found that the discharge is maximized. So this is what we done. First is whatever rainfall value we have computed, if there is any reduction factor, we include those reduction factor. We find out the one-day maximum rainfall values, and then we divide the one-day maximum rainfall value into two 12-hour bells. In first bell, there will be about 75% of the rainfall. In the second well, 25% of the bell. Then this has to be divided into the based on the distribution coefficient of the rain, hourly distribution coefficient of the rain. We have to divide it into incremental value. Once we get the incremental value, we have to go for the critical sequencing. The critical sequencing means the maximum ordinate of the rainfall has to be below the maximum ordinate of the unit hydrograph, and then it will be reverse. And then this is the now storm hydrograph, and this storm hydrograph we will multiply with our unit hydrograph so that we can get the design discharge. So this is the design discharge using this procedure. I'll show you one case example. Say this is again storm we are computing based on L moment frequency analysis. And this is my actual case site. This is the Bargi Dam in MP. This is the Narmada River. So instead of one, we are having a lot of rainfall station within a catchment. There are basically three catchments are there here. One is this Banjar, and this is Morhar, and this is the Narmada catchment below Manot. So these three catchments are there. Within each catchment, several rainfall stations are there. You can see Mukki, Malanjkhand, Mawai, Dindori, Mohgaon, Manot, Mandla, Pamni, Jabalpur. These are the rainfall stations. So when we are carrying out the rainfall frequency analysis for a particular station, based on this rainfall data, we have to compute the rainfall for the entire catchment. So here we are using Thiessen polygon method. So that is the rainfall data is now converted into the aerial data for entire catchment. So that is one way of doing a reduction factor from point rainfall. Now you are converting the for the catchment. So these are the JDI statistics, and this is the plot for a particular station, Malanjkhand. And you can see this is the lowest value is GPA. And here also we can find out through L moment diagram also what is the this GPA is the best fit frequency distribution. So using this GPA frequency, we have computed the one-day rainfall for this Malanjkhand. Just for example, I'm showing, but these are the actual available rainfall data for 1970 to 210 for the study area. And just see for different return period. Again, these are the catchment area is very large. So we are having one-day rainfall as well as we have analyzed the two-day rainfall, one-day maximum rainfall and two-day maximum rainfall. So this is the value for 2-day 48-hour rainfall estimate, and this is the station Malanjkhand. And then we have computed the unit hydrograph for a particular basin. Say we are interested in this Banjar basin. This one is the Banjar basin. So for this basin, we have the unit hydrograph. So you can say this dashed line. This line is the Banjar basin. This one is the Banjar basin. So now my this say for this is the Banjar up to Mani. This 469. This is the 100-year return period. This is 1000 and this is the 10,000. So because this is a 48-hour, so what type of bell it is prescribed? It is prescribed that for every 12 hours there should be one bell. So for 48 hours we will have a 4 bells. So this is the single value in 48 hours. Similarly, we have the analysis for 1 day also. So what will be the value in 1 day, and the second day that will come from the 1 day value also. Means say for this is example 469 is the 2-day maximum, and similar analysis is with 1 day rainfall, so that if it comes to be 300. So for 100-year, first day will occur 300 and balance 169 will occur in the second day. So there will be a distribution for first day and second day. Then again within 24 hours there will be 2-hour distribution. So first 300 days will be divided into 2 parts. First part will be 75% and second 12 hour will be 25% of the 300. Similarly, this 169 again will be divided into 2 parts. First part will be 75% of 169 and second part will be 25% of 29. And then, so this will be the different bell we have distributed our rainfall. And then these are the cumulative, you can say these are the based on the observed data, these are the distribution, cumulative storm distribution. So within first hour this much rainfall has occurred, almost 40%. Next 5 hours means within 10 hours almost 55% of rainfall has occurred. Within 15 hours almost 75% of rainfall. So this way we don't have any event that is we are analyzing 2-day data, but we practically we don't have any data set where we are having 48-hour rainfall. Means if we analyze the nearby SRG site, on the site we could not find any data where the rainfall has occurred continuously for 48 hours. So we will be doing 48 hours analysis, but you can see after 35 or 36 hours we don't have data set. So for fourth bell, we don't have any distribution, means total rainfall has occurred within the 3 bell itself. So based on your actual data, you will, when you are analyzing, you will find the what will be the distribution in different bells. So now we are having the this hourly distribution for 48 hours. And then again, based on this distribution, we will find out the distribution for 12 hours. And then those distribution will be again normalized to 0 to 100, as I showed the earlier example. And then we will plot this. We will keep this incremental value. So maximum will be below the peak of the unit hydrograph. So you can say this is the 1 bell, this is the second bell, this is the third bell. And for fourth bell, we do not have any distribution. So all the rainfall will be distributed within 3 bell itself. When you do the analysis, you will get this type of means cases also. So there you have to distribute within 3 bells. And here we can see this is the peak value we are considering below this unit hydrograph coordinate, and the second highest peak, then third highest peak, like this. The shape of this storm hydrograph is developed, and then we reverse it. So because it says that the reverse will give you the maximum value. So and then we can find out what could be the direct runoff. So just example, this is also a example where we are using for 48 hours, we are using a single peak. And you can see means 24 hour, within every 24 hour there is a peak. So this you can say this is the critical sequencing of the rainfall based on the unit hydrograph. The ordinate of unit hydrograph is maximum at this location, so it has been placed like this. In second case, we have 2 bells of this 24 hour two wells, and then we are having two peak, and these two follows the shape of the unit hydrograph. Similarly, we are having the four bells. This is for case 3, and this is the again the four bell in reverse order. So this way, this is the four bell. So first is smaller, then higher, then smaller, then smaller, then higher. So means different sequencing of the bells, and then corresponding to each we have find out this flood hydrograph. So you just see when we consider a single bell, one bell. So this is the single bell. So single bell, we are getting the peak, but what is happening? The time to peak is increased. So these sometimes it happens, means there are two things. One thing is these are not critical in the sense it is give you excessive rainfall. In nature, this type of events has found to be not occurring. What is mostly occurring is two bell system is there. Now these are basically 48-hour rainfall we are distributing. When we are doing the same thing in two bells, then we can see these triangle marks. In two bell system, you can see the peak is again higher, and of course the time of occurrence has also reduced. Here the time of occurrence is about 50 hours. Here it has reduced to around 35 hours. But again the peak is higher. Now the fourth case is where we have the four bells. In again the sequencing has been changed. So in case of four bell, we are having this type of means sequencing is like this. So we can see two peaks are there, and the peak is time to peak is also reduced. So these are means depending upon the sequencing, we can also get the changes in the final design flood hydrograph. And then the fourth one is the this two again four bells, and here the sequencing is initially the higher one, and then the low, as you said that you reverse the sequence. So this is the with the reverse of the sequence. You can say this is the reverse of the sequence. So here we have the reversal of the sequence. So here you can see the peak of the discharge is also maintained, as well as the time to peak is also maintained. So it was found that with the reversal of the bells, the peak discharge, we are getting a more critical design discharge. So this is what this example shows, and this is what CWC is also recommending in its handbook of design flood estimation. So this is one of the example of design flood estimation. So this is what I have to say in this design flood estimation. If we have any question, we can discuss. Otherwise, we'll continue the next topic, or we'll discuss in the end of this. As you see.
Sir, in the chat box, I think some of the questions has already been answered. However, some people have said that it is an excellent session, and they have requested about the software, what kind of software sir is using, or what kind of software they should use. This is the question they asked. And
that will say no problem. I'll share my mail ID, and if we get some requirement, then I will share. No problem.
Then
so
one
next,
sir.
Yes, madam.
Yes, sir. Sir, Chandra, we will take up the questions at the end now.
Okay, madam.
Yes.
So we'll do that one. I'll just because for these two lectures the time, I think the time is very less. So I will try to cover the second one also. My slide is visible, madam?
No, sir. Not at all. Not present.
Now it is visible.
Not yet. So it's coming.
Okay, thank you. So now we are going to discuss this zoning, floodplain zoning, the approach for floodplain zoning, and we will go through some case study. And basically, there are two methods that is advocated. One is satellite-based, using historical data of the satellite images for inundation, and second one is based on the hydrodynamic flow model studies. So both have some advantage and some limitations. So that also we will discuss. And this is the flood inundation model. Very quickly we'll do. Why we are doing for zoning? So basically the floodplain zoning, when we say it is the restriction on the use of the land, and they are means they are carried out through some legislation, means there are some restrictions through administrative legislation. So generally the term floodplain includes water channel flood, channel, flood channel, and nearby low land areas susceptible to flooding by inundation. And zoning involves the division of the floodplain into specific zones and the regulation with these zones. So what are the regulation? Regulation is the use of a structure or the land. We cannot make a particular type of structure in a specific area. And if you are using or constructing some structure, then what could be the height of the structures and what could be the size of those structures, stability point of view. And what should be the size of the lots and density of the use, because if that zone is under frequent flooding, so there will be probability that high damages will be there, high losses will be there, economical losses will be there. So if we are regulating it with say very sparse infrastructure, and then okay, it will be, we can say that it is okay. But if lot of population is there, then obviously the damages will be high. So that's why these tunings are there. But this is again legislation point of view. We know that our population density is very high, and lot of people are knowingly or unknowingly or under compulsion, they are staying within the floodplain zone, and it is very difficult to remove or give safe places to those people. So at least that is of course one part that we should in long term we should go for floodplain zoning. But as on now, at least we are able to tell them that okay, if you are staying here, you should know what is the risk of staying here, means what is the probability, what is the hazard at this location. So that also is a very means good input to reduce the losses from those area. So in floodplain zoning, first we find out the hazard, and then depending upon the availability of the land and several factors, zoning is proposed. So objective is again for any flood management activity, the objective is to minimize the losses and also have the best use of those lands, so that we can optimum use of those land for our economic development also. It is not possible that we keep those areas unused or unutilized, but at the same time we have to keep those places or the people in those areas also the safe. So that is the basic objective. Now here we are having some of the terms that I will like to discuss. Is first is the flood inundation map. Say inundation is based on the event. If today is a rainfall, so there will be some area which will come under the flood inundation. So that we call it the inundation map. Means inundation is related to a specific event. We call it inundation. So today on August, say for example on August 17, there was a flood in the catchment of the say within the Bharalu River. So part of the area or township has been inundated. So that will be the inundation as on 27 August. So that is a particular date or particular event. Or if I know that, okay, this particular year, this is the maximum rainfall has occurred on a specific day, say day 1. So what will be the inundation corresponding to day 1? So that is the inundation, maximum inundation for a particular year at a specific location. So that is the inundation map. Now, if we have series of inundation map, say we have the maximum inundation for say year 1, 2, 3, 4, 5 up to 10 year, then we will analyze what is the frequency of occurrence of the flood at a particular location. Then what I mean to say that if the inundation is related to the frequency or inundation at any location, inundation map at any location is correlated with the frequency, then we call it hazard. Hazard means at this location, this is the probability, means the flooding occurs every 5 years, every 2 years, every 3 years. Then this area is under flood hazard, under 3-year flooding. This hazard is 3-year flood, 5-year flood, or 10-year flood. So that is the flood hazard map. So basic input for flood hazard map is the flood inundation map. If we have series of flood inundation, we can prepare the flood hazard map. So this is the hazard map, means we have the extent of inundation as well as some quantification that, okay, these are the frequency of inundation. So this will give you the hazard map. Now within the hazard map, there are several places. See, in the middle of the river, the flood is occurring every year, but there is no risk because there is nothing is there where there will be the bad effect of the flood. Means if there is some human staying at that mid of the river, then we can say, okay, this hazard is risky. But if no human is staying at that location, we can say, okay, it is hazard. But because no one is staying there, there is no risk. But again, on the bank, if within the same flood hazard, if someone is staying, means there are some man or some structures are there, which is probable or which is likely to have some damages or some losses, then we can say, okay, there is some risk. Means if some economic values or some loss of life is associated with the hazard map, then it will be like a risk map. Means in hazard map, this is because of the natural event. In risk, in addition to the natural event, if we add some you can say element on risk, which is having some economical values, then it will be a flood risk zone map. And then from the flood risk zone map, we prepare, if we categorize the regulation that, okay, we don't permit such activity in particular area, we don't permit this type of activity in this area, then this is the floodplain zoning map. So this way, gradually from inundation map, all these maps can be prepared. So this is way from satellite images we are preparing this floodplain zoning map. The flow chart is again like this. We are having from remote sensing technique, we are having the inundation map. If frequency is added, we can get the flood hazard map. And if we are having some economic aspect, actuarial inputs or financial aspect input, then we can develop the flood risk map. And then some administrative regulations are imposed, then we can prepare the floodplain zoning map. So I'll give you one example of flood hazard mapping for river reach of Ganga between Buxar to Mokama. This is what we have discussed earlier is generally it is based on the satellite images, inundation map. Now this I'm going to tell you about the mathematical model approach, means flood inundation modeling approach. What we are having, we have the observed discharge data at particular location, and then we go for the flood frequency analysis. We find out what is the flood of various return periods, and then different processes of this flood frequency analysis will be finding out the best fit distribution and then identifying those distribution and then using those parameters to forecast our data set to give the estimate for various return period. So this is about the flood that is going to occur in the system. Then the catchment response, we have the distance elevation model. Here we are using the river flow model, means within the river, how the flow is propagating, that we are going to use the HECRES model. So for HECRES, we are preparing the different data set, what is the river cross section, what is the river alignment, what is the boundary condition, all these we will develop in the HECRES model. And then we will try to run our model and for a particular inundation, and we will get what is the model output. Then on the other side, we have some historical data set, means say I am simulating a flood of 1996, extreme value of 1996. So from this actual value, I am using the 1996 flood data. My rainfall, this HECRES model, river flow model is there. So I will simulate the 1996 flood in this model. I will get an output. What output I will get? I will get an inundation corresponding to 1996 flood in the system. This inundation, I will try to correlate with the satellite images. During 1996, I will try to find out what is the maximum inundation that we are getting from the satellite image. So corresponding to this event which I am simulating in the model, I am also having the satellite image. So now I will compare the output of the model with the satellite data, and I will try to find out, okay, how much error I am getting in my flow model simulation. So generally we are getting some error because of several issues, several limitations of the study. Generally we don't have the proper data set input for the model, so that we will always have some limitation and we will get the differences. So that is the gist of the work I'm going to show you. So this is the main red line. This is showing the main Ganga river. This is somewhere Buxar is here, and we are having 4 tributary within this reach. This is about 250 kilometer stretch is there from Buxar to the Mokama site. On the right hand side, we have the Mokama site, and 4 tributaries is Ghagra on the left bank and Gandak river on the left bank, and right bank we are having Son and Punpun river in this stretch. So what we are doing, first we are having the flow model. For this we have developed in the HECRES, and whatever data available with us that we have used the Survey of India topo sheet, Central Water Commission cross section data, and some additional data for embankment etc. that we have used. And we have the discharge data at this location. These are the gauging sites up to which we have considered the this river. Here we have Sripalpur, here we have the Vaishali, here we have Koilwar. These are the different gauging sites where we have the data of different year, during different year. So using those annual peak, we have find out what is the discharge for various return period, and also for a specific year also we have data, so that also we have used. Now based on the L moment, we have computed the return period of various stations, Buxar, Gandhighat, Koilwar, for different return period, 2 year, 10 year, 25 year, like this. These are the you can say 2 year return period. Okay, these are the different year return period that we have estimated using L moment approach. And this is the this study has been carried out long back. At that time, ArcGIS was ArcView GIS. So here we have all the data set available from Survey of India topo sheet, and that we have used. In addition to this, some elevation on the embankments are also there at that time. So that also has been used. So based on this, we have prepared the digital elevation model of that area. And we have simulated this peak flood of 1997, and this HEC model, they give you the inundation map for 1997. So blue line shows the inundation map for the 1997, And corresponding to that year, we have also got the satellite images, and we try to find out, compare these two images. So we found that a gross error of 8% is observed. Of course, at some of the locations, the differences in inundation extent is very high, but the gross error was 8%. And obviously, this is because of the very limited data set for that area. And again, we got for similar inundation for 1998. Here we got the 6.9% error in that area. So these are the IRS1C images that we are getting inundation from using our ADAS image, and this is the inundation which we are going from the HECRAS image. So this way we have completed, we have carried out this inundation. Now, once we establish that, okay, with the observed data set, my model is working well, then I have run the flood of various return period at all the tributary, and to find out what is the inundation for 25-year flood. So this is the inundation for 25-year flood. We can see this is the inundation water depth, and this is the spread area, total area. So for various water depth, we have the inundation extent. Similarly for 100-year, and again we have considered the flood corresponding to the danger level at that time. So this CWC defines the danger level of all the sites, gauging sites. So what could be the at danger level, what would be the corresponding return period flood? If the water level touches the return period, what could be the corresponding equivalent frequency of the flood? So that frequency we have used at all the sites to compute the extent of inundation. So that way also we have find out the extent of inundation. And then also we have carried out one risk analysis that, okay, if we are using 25-year return period flood, T for 25, so what is the probability, what is the risk that this 25-year flood occurs within a span of 10 years, n years, within a span of n years, what is the probability or what is the risk that 10 year within 10 year that 25-year flood occurs? So that way also we have find out what could be the extent of inundation. For example, if we see this is the risk of, we can find out the risk of 25 years when n is 10 years. Within the 10-year span, the risk will be 25 year if 25-year flood occurs. So this way we also try to find out the extent of, means we say that, okay, 25-year flood, there is a probability that it will occur once at least in a 25-year, but what is the probability that it will occur within the next 10 years? So that way, that is the risk we are corresponding to those risks also the inundation is computed. And this way we prepare the, for various return period, what is the area of inundation in various depth classes. And we can say this is the for 2-year, for 10-year, 25-year, what is the inundation all along the study stretch. So this way we can find out that, okay, if 50-year return period flood is there, we can find out, okay, what are the reason, what are the area which is going to come under inundation. For 100-year, what are the areas going to come under inundation? So that way we can find out the hazard map for 100-year. Zoning, we don't say anything because zoning is not only the engineering part or the scientific part, but it is more on the political part. We cannot say that means until unless policymakers are involved, zoning is to be defined that way. But from means engineering side, you can define that, okay, these are the hazardous zone, and these are the area which may be affected within this zone. So up to that. Again, one satellite based and also this modeling based also one approach is there for flood mapping for Jamuna River near Agra. This study is also carried out at NIH under this NGT direction, and we have to fix that the floodplain either for the 50-year return period or the maximum flood that has occurred during last 25 years. So what we have carried out, we have carried out the the analysis of the data. These are the you can say the flood level and discharge data available for one of the site. Powai gauging site is there, and for last several years, and then 1970 onwards, 1960 onwards, and then we plotted this rainfall. We plotted this rainfall and runoff data to get a relationship between discharge and flood level. This flood level, and this is the discharge. So we find out the relationship between the flood level and discharge. Why we are interested in level? Because whenever we are finding out if peak flood or the design flood, say this is 1979 flood, this 25-year flood was smaller, so we have to go for the 1978 flood, that is the actual event, and it was around 8900 meter, and by analysis we found that the return period of this 78 flood is computed as 233 years. So either you go for this 78 flood is 238 year, while the within the 25 year this 210 flood has occurred, so that was the frequency of 79 years. So we have used 210 because the direction was to use either the maximum flood within 25 year or the 50-year flood. So this was the higher one, so this we have taken as the flood for which we have to go for the floodplain mapping. And then what we did, corresponding to this flood, we find out what was the level in the river and the date for corresponding to this flood. For that date, we collected the satellite image, and then the satellite image, on the satellite image we mark the inundation from that data, and then that inundation is corresponding to 2010 flood. It means it is corresponding to 79-year return period flood. So that was the one means case study that has been carried out. The gist you can see from this map is we can found that lot of activities has already been occurred within the floodline map, and this is the 18/11/2010 floodline, and lot of within this lot of means activities or infrastructure has been developed, so that we have to mark, and then accordingly it has to be means that floodline is to be established in the this system. Then another approach for satellite-based image, satellite image-based flood zoning is we have the inundation map for various years. So we have a stack of binary flood maps, and then we find out the annual maximum series from the flood level data, and then we find out the probability for different flood level, and then corresponding to those flood level from this library of this flood maps, we find out what is the flood map corresponding to a specific flood level, and then that will be define you the flood hazard map for 25 year, 50 years. So this is the approach that we have used in that study. So we have during this actual 2010 flood, these are the various satellite images are available. Exactly the flood has occurred on 26 September. So we have the 26 September, this IRS-P5 data was available. And on 27, multispectral data was also available with spatial resolution of 15 meter and 30 meter. So this we have used, and this is the rainfall during those days, and this is the water level during that one. So this is the maximum water level for which we are carrying out our analysis. And another data in the means these are the data which we have used for the inundation, and this study was carried out during 2017. So what are the area that is comes under this flood plain? So that for that we have used the Google Earth images and very fine resolution Google Earth images from 23rd January 2017 data was there. So this inundation map was superimposed over this image, and we find out what are the area which is under inundation. So for example, you can see we have used the water pixel using ADAS images, image processing, and GIS we have carried out in ArcMap, and we overlaid bank line for 79-year flood over this Google Earth image, and we find out what are the area exactly which is within the inundation. And if some structure or something is coming under this inundation, then we have marked. So these are the area which is coming under inundation, and along this area we have marked the pillar also. So these are on the ground, these pillars were marked, and these for administrative means use. So Agra Development Authority, they have used this pillar so that no activity will be permitted inside the river from this pillar. So this pillar is the boundary. Pillar onward, you may do some activity, but within the pillar up to the river, there is no activities is allowed. So this way, this work is carried out. Part of this structure, you can see some of the developers, they have constructed retaining wall and they are trying to develop these areas. So that also has been marked. Like this is on the ground. This is from the satellite image. You can see some retaining wall is there. Here you can see this retaining wall, and they are developing this area also. So this you can see this is the retaining wall on the here. So this type of encroachment, etc., we can find out using this approach. Now the comparison of the two approach, satellite based and modeling approach. The data is easily available and cost effective. Analysis takes lesser time. Real river profile, physical condition during historical extreme flood is affected. Okay, what is happening? Modeling is generally preferred where a lot of changes has occurred in the river system. And if during historical time or the using satellite images, those means changes are not possible, or the future changes, if I want to simulate what will happen during future, then it is possible through modeling approach only. Then inundation maps are discrete in nature, means for some of the dates you may not get the inundation. Projections are for future change in developmental activities along river or meteorological forcing is difficult to incorporate. Flood hazard is estimated based on flooding depth or extent of inundation. And it is micro level planning, it is suitable, but here it is if your river is very dynamic and lot of activities are there, then for macro level and futuristic planning we should go for the modeling approach. So based on this we could find out some of the benefits and some of the limitation of these two approaches. So this is what I have to say about this journey. So now we can discuss some questions.
Thank you, sir, for the good lecture. And many people have commented.
Yes, madam. I'll take one by one.
Sir, yeah, many people have commented about the excellent session, and they all have appreciated your presentation. And some people also like your presentation, the PowerPoint presentation. But I hope we are currently giving YouTube channel also. The link for the YouTube is given in the chat box. Kindly see the YouTube.
I see the comments in the chat box.
Sir.
Okay. One question is by Manjeet. Can we get presentation material by email? So what I can do is I can give my presentation to the organizer, and then from there you make some mechanism to transfer to the participants if someone is required. Okay, madam.
Yes, sir. Thank you, sir.
So the email by presentation email. Case study for flood frequency analysis, which software you are using. We are having one inbuilt program for this L moment based frequency analysis. Otherwise, a lot of softwares are online available. Some MATLAB programs for L moment based program is also there. So if you are interested, I can give you in NIH, Dr. Rakesh Kumar and many more scientists are doing it. If you are interested, we can give you the contact number. So that also, if someone is interested, they can write Dr. Rakesh Kumar and rakesh.nih@gmail.com is his email ID. So you can ask him, or in the NIH website also, probably some softwares are there on NIH website. So from there also you can, it is NIH Roorkee, roorkee.gov.in. So there also we can get it. Some related case history may explain well. I try to give you some case studies, but again the case studies are also so extensive that it is not possible to include in 2 hour session. So some of the reports are also there on the NIH website. Almost all reports are there in NIH website. So related with the flood frequency or design flood hydrograph, if someone is interested, they can go through it. Or if you want some specific from me, you can mail to me also. My mail ID is mailofpmoney@yahoo.com. So I'll write here. So if someone is needs some specific information, you can mail to me. I will give you reply you, and I'll send you some attachment. Okay, then for statistical parameter, I said L moment based frequency analysis. And why uniform swell loss? Actually, swell loss is not uniform, but when you are considering the design flood, when we are trying to maximize everything, we are considering the means soil to be fully saturated, and in that case we are going to have this uniform soil loss. Flood estimation is giving values of the loss rate and best. Yes, the flood estimation report of CWC, actually what they have done, they have carried out or they have developed the flood estimation report zone wise, means all over the India they have divided into different zones, and for different zones they have the flood estimation report. And these soil loss rate and base flow, they have given different values depending upon the zone. So there you can refer it, and you can get it in the CWC website under publication. Different flood estimation reports are there. Sir, can you give us some reference material and resources for further study? Yes, further study, lot of references are there. You can just see this flood estimation report by Central Water Commission 2001 is a very comprehensive report, where you will find a lot of means exercise, case examples, as well as guidelines also, so that you can refer. Otherwise, on NIH website also you will find a copy of the list of the publication or list of the reports that we have carried out for real case studies. For at some of the case study, you can also for design flood estimation, you can also get at the CFMS Guwahati center also. Those who are nearer to the Guwahati center, they can refer it. Otherwise, on NIH website, those means including Guwahati reports, lot of studies are there. Okay, and PPT, regarding sharing of the PPT, what I said that I'll share it with the organizer, and from there you can take it using some Google Drive or something like that. Can you please let us know by using which software prepared the map? This map we are preparing, just see, I said that in HECRAS, after doing the modeling, there is an option to prepare the inundation map. Again, in nowadays we are also doing in Mike. So in Mike also, in 2D as well as Mike 1D also, you can prepare the inundation map for your simulation. So for modeling based simulation, inundation mapping, you can use your HECRAS as well as Mike. And for satellite based, generally we are doing image analysis in ERDAS. So we can you can also do it in ERDAS, and all the GIS analysis we are doing in ArcGIS. So ArcGIS is also used for image processing, but we prefer image processing in ERDAS. So you can do in ERDAS. And HECRAS is inundation mapping is only for uh, modeling based inundation. Satellite based, we cannot go for HECRAS. We have to go either by ArcGIS or by ERDAS. So this is about the inundation. Is there any guidelines how to set danger level with respect to design flood level? No, design flood level is not for the danger level. Danger level is means design flood level where you are going to design a structure. Then for what flood you are designing a structure, that is the design flood level structures. And danger level is generally CWC is doing this. Carrying out this activity, danger flood level. So based on the historical data, whatever the maximum flood level has occurred, they demark it as a danger level. So, so recently with the lot of climate change, at many locations you will find the water level, and also because of the embankment, construction of embankment, you will find on many years the flood level is higher than the danger level. So danger level is generally the maximum flood mark that has been decided by the CWC as a danger level. But nowadays you can find many of the gauging sites, they crosses danger level. And this is mainly because of the lot of changes are there, even on meteorological, means climate effect also is there, and also because of the embankment. So if in the downstream there is a embankment, so you can assume that for a smaller discharge also, now the water level will be higher and it will crosses the danger level. So this is not P Money Yahoo.com, madam. It is mail of P Money. Okay. Sir, many times you have to combine the dam release with rainfall. How this is tackled? Again, in modeling approach, there is some means in modeling approach, there are a lot of options are there where you want to include the dam release or even dam break or even the river flow also. So there you can include within the river, means a lot of we have also carried out a lot of simulation work, mathematical model based study in which releases from the dams are also accounted for. Recently, we are doing one study for Nuclear Power Corporation at Kaga site. Kaga is in Karnataka, and there the means peculiar thing about that site is the plant is in the upstream of the Kadra Dam, while their colony is in the downstream of the dam. So what is happening? The design condition for the plant side, because it is in the upstream side, that is means that is one way is very harmful to the, or very means critical to the flooding at the downstream side. So while we have to decide the safe grade level for the township, we have to also consider the release from the dam. So that we are doing in my flood. So there are several ways to include those type of situation or incorporate those type of situation in the modeling. So in addition to the design flood in the river, and for nuclear power plants, the design floods are very high. Generally, we are using 10,000 return period flood. Means in normal course, BIS recommends maximum up to 100-year return period flood. But in AERB, there is Atomic Energy Regulation Board guidelines are there. So for nuclear power plants, they are using 10,000 year return period. So in addition to the 10,000 return period flood in the river, they also include the release from the dam. So that is also incorporated, and we have to carry out the analysis. So that is one of the case study that we have carried out. Can you share details procedure of flood inundation mapping? There are a lot of hands work are there and notes are there. There you can very easily, means it is very they have written in a very simple language and very means uh, easy steps. So probably you can go through it and you can get it. And if you wish, I have also downloaded it from their site, US Army Corps of Engineer. You want it to be shared, I can share it, but on their website it is freely available, so you can also download it. So these are the comments, several comments in the chat box, which I can see, and I try to reply to the best of my understanding. If anyone is having some other specific question.
So I think all the questions that have been put up in the chat box has been answered by our resource person. And for further any details, you can contact us or you can see the website of NIS Patna, as well as Roorkee for further detailing. And so thank you so much for your very thoughtful deliberation, which is currently very much required to handle the flood management. And to all the participants, tomorrow we'll be opening our Cisco website by around 10:30. We will be having 2 classes again regarding the evaluation of riverbank erosion using river flow model, and the other one is urban flood modeling, which will be delivered by B. Chakraborty sir, and again from NIS Patna. Sir, I would like to request our course coordinator, Dr. U.M. Hazarika sir, to give the last line, sir.
I would thank our resource person, Dr. Pankaj sir, for this nice deliberation. In detail, he covered the 2 technical session, and including the compliances given in the box. So I am also thankful to all the participants for attending the training and also interacting the resource persons. So if the trainees have any specific doubt or if they want more clarification or more about the flood management, they can again go through the materials that our resource person will like to provide and share with you. And also they can visit the websites of the National Institute of Hydrology, CFMS, Patna, and the Roorkee website also for further knowledge. And there are many reference book and guidelines and materials are available in the Central Water Commission's website, our ministry's website. They can also go through that. And that our institute, Neriwalam, and this National Institute of Hydrology, and we are this and also disseminating the knowledge on flood management, the masses. So with this, we want to conclude today, and tomorrow we will be having another 1 day mostly on non-structural measures, on which our experienced and renowned resource person deliver. I request all the participants to join tomorrow also. Today I have seen many participants also joined in YouTube live